Hello everyone, welcome to ECE6414 Analog Integrated Circuit Design for Spring 2016. I will be your instructor. My name is Meysam Govanlu and you can reach me at mgh@gatech.edu. Today I'm introducing the course by going over the course syllabus, and you should feel free to ask any questions you might have. There is also a PDF of this syllabus with more details posted online on the course syllabus, and I highly recommend that you also go over that written document. So let's get started. Here's the overview of this lecture, this introduction. I will talk about the importance of analog IC design by going over one example from my own research. It's a system on chip called WINER, which stands for Wireless Integrated Neural Recording System. You might know that I do research on implantable devices and medical instruments. So most of the research in my lab, Georgia Tech Bionics lab, is related to these kind of topics. And then at the end, there is a word of wisdom from one of my good friends at Medtronic, Dr. Tim Denison. And with that, I conclude this lecture. So, talking about wireless neural recording, you know that brain is a very complex circuit. It consists of 10 to the power 9 to 10 to the power 12 neurons, depending on the species. In humans, we have 10 to the power 11 neurons in our brains, and each neuron makes about 1,000 connections known as synapses with other neurons. So network brain is like a huge network, and all these amazing capabilities of the brain is due to this dynamic network, dynamic circuits of the brain between different neural populations. And in order to explore the brain and understand how it works, many researchers have been working, and this type of research has been only accelerated in recent years, and there is a renewed emphasis on this all over the world. And if you think about trying to record the electrical activities of the brain, you can understand that those researchers are really interested in learning more by recording from many different channels in order to get a good overview of what is going on. And the size of the brain is also important. So here, for example, I have compared the actual size of a mouse brain in comparison to that of human. So with such a complexity, you can understand that there is a big desire to have a large number of recording sites. So this type of research has been ongoing for many years, and it has even been conducted on humans, recording from about 100 channels in 2006. Lee Hochberg and his colleagues showed that it is in fact possible to record from the brain and use that signal. You see all this signal processing going on, and move a mouse cursor by just users and the patient's thoughts. This is a person completely disabled from neck down, but thanks to this brain computer interface he has been able to convey his intention to the computer. But mostly this type of research is done on animals. Currently most labs they have hardwired systems, and the animal needs to be connected to the system through wires, and this can change and affect the behavior of the animal. So we are trying to develop a multi-channel wireless neural recording system that will be very helpful in animal experiments, but also eventually in humans, because of course this is not very practical to have a connector on top of the head. This is very dangerous and very prone to infection and damage to the device and to the brain. So this whole thing, the neural recording system needs to be wireless and fully implanted in the body for a practical brain-computer interface, and that will increase the mobility, user comfort, reduce the risk of damage, infection, and also aesthetically more acceptable. So this is the big picture, the block diagram or the overall diagram of the system that we are developing. This system is not only able to wirelessly send the neural activity to the computer and demonstrate it to the end user, which is the researcher, but it does not require the animal to carry a big weight of batteries. So this system is also being wirelessly powered through an array of coils that are around this recording or experimental environment, and that's a system which we call inner cage system. And if you are interested in that, you can read about it through the publications out of my lab. So here you can see the block diagram of the Wiener 6 system. It was presented at ECE6414 2010. We are now working on Wiener 8, so this is a couple of generations old, but for the purposes of this course it can give you a nice overview of the kind of circuits that you can implement on a system on chip and make a wireless neural recording system happen. So these are the multi-channel electrodes, micro electrode array, which are developed through micro machining, or they could be some thin micro wires. We have 32 separate channels, and then you have an array of parallel low noise amplifiers here. There is a secondary amplifier that does additional amplification as well as filtering, and then in this particular architecture we do analog to time conversion. So we have a circuit that converts the analog information in the neural signal to a pulse width and convert it to a pseudo digital waveform in order to be more robust against interference and noise. And then we multiplex all these 32 parallel channels with some additional information such as band gap reference voltages, the rectifier voltage to close the power control loop, the temperature, and the negative power supply. So a total of 36 analog channels are multiplexed and form a PWM signal. Each pulse is related to one of these 36 channels. Then this pulse is masked and derives a voltage controlled oscillator to generate a frequency shift kit signal at a high frequency. In this version we use a frequency around 900 megahertz that is transmitted through a power amplifier and antenna. On the other side we have a custom designed receiver with an RF front end and its own antenna. It has a down converter, converts the signal to baseband, and then recovers that time division multiplex pulse width modulated signal and feed it into a field programmable gate array that converts that pulse width by measuring the width of the pulse width to a digital output. This block we call it a time to digital converter. The overall function is analog to time and then time to digital, so the whole thing works like a multi-channel wireless analog to digital converter, and the digital data is transferred to the computer through a USB and demonstrated for the end user. You can read more about this system in our related journal publications. This is the chip fabricated in TSMC 0.35 micron, if I remember correctly, and the size of the chip is about 4 by 6 millimeters. Here you see the test setup. This is our custom receiver, the receiver antenna. This is the chip with Winner 6. It's a packaged chip, and this is small antenna does the transmission between this antenna and the receiver antenna. But as I said, the chip is wirelessly powered. I forgot to mention in the block diagram that we also have a power management block that receives this inductive power. There is a full wave rectifier, a low dropout regulator, generates a stable DC voltage to power the entire chip, and this is also part of the entire system on chip. As you can see, everything this is an array of low noise amplifiers, filters, and comparators that you saw. This is some digital circuits and shift registers, reference generators. We have a low noise, low dropout regulator here, an over voltage protection, the rectifier, power amplifier, and the voltage control oscillator. They are all integrated on this chip. So back to the test setup. Here we have the inductive powering. This is the power amplifier to drive the inductive power transfer at 13.56 megahertz, while the data transfer is conducted at 900 megahertz. In this particular test, we have generated the signal with a function generator. Only a sinusoid is being transmitted, and you can see that the data is received and delivered to this PC, and all 32 channels are working fine in this benchtop setup. But we did not stop at benchtop testing. We also tested the system in collaboration with Professor Mans at Emory University. So here you see the Winner chip mounted on the head stage of this rat. The rat is encouraged with pieces of chocolate to walk around this track, and while the receiver, a dual input multi-antenna receiver, which is an extension of the one that I showed you with 4 antennas, is placed around the track in order to make sure there is no blind spot in this track. So what we did was the recording, placing the electrodes in a to record from certain neurons that are called place cells, and these cells are sensitive to the position of the rat on the track. So you can see that these neurons are only active, and their firing rate goes up when the rat is at a certain position on this track. These are the same type of cells that tell you where you are, give you a sense of position and placement when you are in a room or in a city. And recently the explorer of these place cells received a Nobel Prize. Here you see a comparison between the hardwired commercial system and our wireless system. So you can see that even though the signal received by the winner system is a little bit noisier, but the position is exactly the same, and it shows the functionality of the wireless motor recording system. So this was an example of what you can do and the kind of systems you can develop with the information that and the things that you learn in this class. Of course, there is a big motivation in implantable devices to make the system as small as possible, to make it minimally invasive to the host, human or animal. But there are many other applications in your smartphone, in your computer, in a car. You always are interested in more integration and lower power consumption. So let's go over the course syllabus now with this example of system on chip, showing the importance of analog integrated system design, which is the main topic of this course. So the course web page is listed here. You will refer to this website very often, because all the lecture material and the reading and video assignments will be posted on this website. So please bookmark this website. It also has a course calendar that, as I said, I will post the exam solutions, the reading material, the slides, and everything related to each lecture, each session on this calendar. And as I mentioned earlier, the syllabus is also posted both on a separate page and as a PDF. Fortunately, the textbook that I use for this course also has its own website in which the author of the book posts his own lectures. Actually, I will use the same videos for my course, and also class notes and additional material, as well as CAD files for the examples and solutions, and even some of the homework solutions. So this is another website that I highly encourage you to bookmark and refer to it quite often. Prerequisites for ECE6414 are ECE3400 analog circuit design, and ECE4430 analog integrated circuit design. I often teach both of these courses myself, but there are also other instructors teaching it. So you should either have taken these two courses or the equivalent of these courses at other universities. You can check the course syllabus by going to my website, look at the teaching page, and I have links to the websites of these courses. Also, if you go to the 6414 website, on the last page I have links to related materials and the archives of both 4430 and 6414 itself. I recommend that you look at those, especially those of you who want to move a little bit ahead of the class itself. So my assumption is that you are quite familiar with the circuit theory and concepts such as frequency response, small signal model, and analysis. You should be familiar with solid state devices, p-type, n-type semiconductor, p-n junction, bipolar transistors, and particularly MOSFETs. Most of the emphasis in this course and in today's integrated circuit technology is on MOSFETs and especially CMOS because they are most cost effective by a large margin. And in addition, some very basic building blocks which are covered in 4430, such as current mirrors, reference generators, single and multi-stage amplifiers, and basic op-amps and differential amplifiers. Again, you should have seen these in your earlier courses. If you are new to any of these basic building blocks, perhaps you should take 4430 before taking 6414. And also because I will not have time to cover MATLAB and other CAD tools, you are expected to know how to use these tools both for homework as well as the final project. The textbook for this course, as I mentioned, is written by Professor Jake Baker. It's called CMOS Circuit Design, Layout and Simulation. I usually refer to the third edition of this book. Excellent book. The author has received the IEEE Medal of Education for this course and for his lectures that he has put online for us to use. And it's excellent material, very up to date and very helpful. This book is like an encyclopedia of CMOS circuit design, and I highly recommend it to you either in electronic form or in hard copy. There is a second textbook that is not required but highly recommended by Allen and Holberg. This is a previous textbook for this course, but it's we refer to it once in a while, and sometimes I find good homework problems or exam problems from this book. But there are quite a few very good books in analog circuit design. There is definitely no shortage of good material written on this very important topic. The most famous one is by Gray and Meyer, analog analysis and design of analog integrated circuits. Professor Razavi at UCLA has a book on design of analog CMOS integrated circuits. And those of you who are interested in doing professional layout, I can't emphasize enough how important layout is in designing good analog circuits, considering the importance of parasitic components, especially if you are doing high frequency design or ultra low power design. So the Art of Analog Layout Design by Alan Hastings from Texas Instruments is highly recommended. And finally, another very famous book by Jones and Martin called Analog Integrated Circuit Design. As you can see, there are quite a few very good books that you can refer to for this class. As students, I know how important grading is for you, so right off the bat, I would like to show you and tell you that about 50% of your final grade comes from the final project. It's a very comprehensive, time consuming, but highly rewarding project that will be done in groups of 3 students. And then the other 50%, 10% comes from your homework. We will have between 4 to 6 homeworks, and in the new design of this course, homework is also done in groups, and I will describe the homework a little bit later. There will be 2 midterm exams, one of them 10%, the other one will have 15% of the grade, and this will be a total of 100%, but I also leave an extra 5% credit for those of you who demonstrate active participation in class and come up with the most innovative ASIC designs for your project, and those of you who provide me with good feedback on how to further improve this course and make it more rewarding and conducive to learning. The project itself is divided into a few items that will be executed in a very strict and well-designed procedure and timeline. Draft 1 5%, draft 2 10%, layout 5%, circuit performance has 10% of the project grade, and then at the end of the semester, instead of a final project, a final exam, we have final presentations, which is kind of like an oral exam. This is also done in groups and will be conducted in the form of a conference session. In addition to that, we have a final paper that is 30% of the final grade, and it should be done in IEEE format. And finally, we have simulation results 10% and group cooperation, which is the grade that you give to your group mates. So the way that the class will be conducted is using lectures that will be that basically are pre-recorded. As I said, these are lectures given by Professor Baker, the author of our textbook. In addition to that, you will have reading assignments, collaborative homework, in-class activities, discussions, and a wide variety of active learning interactions. So what I'm doing is moving away from the traditional passive learning environment that basically the instructor is speaking all the time, and there is a one-way flow of information from the instructor which has all the knowledge to the students. This is shown that is not the best method of teaching and learning, particularly in these more complex subjects such as analog integrated circuit and system design. Instead, we will have a dynamic learning and active learning and interaction in a way that I will basically encourage interaction between students. You learn the material even before coming to class through these pre-recorded lectures, and then it will open up a whole lot of time in class for us to spend on problem solving and interaction among the students, having discussions and basically creating a much more dynamic and lively interaction requiring participation by all the students who are in class, as opposed to just some more active students and the rest of them not quite learning the course material. There is there is little emphasis on memorization and more emphasis on true learning and experience, hands-on experience, at least at the circuit design and simulation level. So my role is more like a guide and coach during our lectures, and that's basically how I will conduct a class. We will have some quizzes at the beginning of the class, usually once a week, and as I said, we have a lot of good activities in class that would encourage learning. The course contents will be an overview of the prerequisite material, just to make sure everybody is on the same page and refresh your memory. Then we will use these IC building blocks that are part of the prerequisite in order to construct analog IC systems such as data converters, filters, and mixers. Then we will review the characteristics and specifications of these blocks and you will hear this term mixed mode circuits, that are a combination of analog and digital. Usually it's referred to data converters. As I said, this is a highly project-oriented class, so we will spend some time discussing the projects and the kind of problems you face, and we try to address those collectively by sharing different groups' experiences and discussing them in class. So you will have hands-on experience and a lot of interactions among your group and between groups, including discussions over your ASIC designs and post-layout simulations. So in addition to the basic fundamental course material, you learn organization, attention to details, engineering compromises that you have to make in order to make your system on chip work. You learn how to optimize your circuit. You learn how to manage your time, especially because this is a time-consuming course, and it become a bit challenging towards the end of the semester. So I highly recommend that you stick to the timeline and don't procrastinate things to the last few weeks of the semester, because the project, and you might have other courses, the projects can get quite heavy and time consuming. You learn how to effectively collaborate and communicate among the group that you will form. Good presentation skills, as I said, that's a big part of your final grade, especially the final presentation. Effective teamwork, and all of these will be in addition to the fundamental concepts and topics in analog integrated system design that you will learn from the textbook and video lectures and through homework. So there are reading assignments. Assignments will be posted on each week on the assignments page. If you look at the course website from this page, from the author's website. In addition to that, there are sections of the textbook that will be identified for you to read every week. Sometimes I post journal papers and you need to do some literature search, of course, around the topic of your project, and I will go through the detail of the project in a little bit. Assignments for each week will be included in a quiz. I try to hold the quiz on Mondays, but it could be any other day. They will be pre-announced, and you will do it using T-Square online. So please, on the days that you have a quiz, make sure to bring a notebook or a tablet with you in order to answer the quiz questions in the first 15 to 20 minutes of the class. I will not give any handouts in class. Everything will be posted on the class web page, and you are responsible for downloading and printing them or looking at them on the screen when you come to class. The homework will be assigned to the team. So you can either decide to divide different problems between different members of the team, or each member can do the entire whole problem set and then compare your results with one another and come up with the best combination of these solutions. You will send the homework before the deadline to me following this particular naming. So I expect to receive PDF files with this particular name with your team number and homework problem set number. Then I will assign these homework randomly to other teams. So members of each team will grade the other team's homework and write a one-page summary of what the other team should note. So in addition to grading, they write a one-page summary about their mistakes and how they should be corrected. So your final grade out of each homework will be a combination of the grade that you get from the homework itself and the grade that I give to your one-page summary. So these two components are equally important, and basically you are encouraged to grade your other classmates' homework very carefully, and also write that one-page summary very carefully, because this is shown to be one of the best methods to learn the course material and also learn from other people's mistakes. I will post those one-page summaries on the website for everyone to see what the mistakes are and what the best solutions are. We will have 2 midterm exams. These are closed book, closed note, each of them 50 minutes in class. and you can bring one sheet of equations and anything you want to write in those sheets on both sides, plus in the second problem, the last sheet you prepared for the first problem. The exams are cumulative, and the second exam is almost pretty much the entire material that is supposed to be covered in this course. All grades will be final a week after the exam is returned to class, and if you miss a midterm or a quiz or not attend your final project presentation, a 0 will be averaged into your grade. Here is the project timeline. It will be very strictly followed. You will form groups of 3 students. We have had groups of 2 students in the past, but in order to be kind of fair to everyone and divide the workload equally among all members of class, I highly recommend that you form groups of 3 students. My experience shows that the team that you form has a significant effect on your final grade. So it's very important that the team members are that have a cohesive and good interactions. The same way that you don't choose your co-workers when you start working. For those of you who do not form your own teams, I'm going to form the teams about a week after the students who take the class for credit are final. So it's going to be the second week of towards the end of the second week of the semester. So the first milestone is called draft 1, about 4 weeks through the semester. This is a 2-page document, not including the references. It will include a rough block diagram of the complete analog mixed mode system on chip that you will be designing, showing the inputs and outputs of each block, on-chip and off-chip components, and a description of the entire system. You should also support your claims and the materials you have with references. Do not include the references that you haven't read, but the list of references will not be counted towards those 2 pages. In those 2 pages, you also need to mention what roles each team member will play with respect to the design and development of those blocks. Also, you among the 3 team members, one of them should be the point of contact. So I expect to receive emails and the deliverables from that particular member, but every email, every correspondence with me regarding the project and the class, you should also carbon copy the other team members to make sure everybody is in the loop, because I will not accept someone to say that I was not aware that, for example, the deliverable was not submitted or delayed, or this is not what I meant to submit. All the group members should be copied on all the email correspondence for me to consider that email as a legitimate email from that group. And you also, through literature review, need to understand the state of the art in the area that you choose to develop your system on chip and do your project. Even though the specs that you pick for your design does not need to push the limit, because you have a limited time, and we do not necessarily need to go beyond the state of the art. After draft 1, you will be the next milestone is draft 2, about 8 weeks through the semester. For draft 2, you have done a much more thorough and comprehensive literature search to come up with the specific analog IC designs, topologies, building blocks, much more detailed specifications, and the kind of functions that each block should perform in your system on chip. And you also need to include a summary of the literature review. Basically, what is this system good for, what is the state of the art, and what is it that you are going to implement and deliver by the end of the semester. You have 7 pages for this draft, not including the list of references. Even though it's not required, I highly recommend that you include some system level simulations. I don't need to see transistor level designs for draft 2, but you can use ideal components such as an ideal op-amp in order in Cadence, MATLAB, or Simulink environment in order to demonstrate the system level functionality and the overall idea and concept of what you want to implement. That will guide you to better understand the design targets and design specification, and also it is shown to help with your system level design quite a bit. So you need to have a detailed list of design specifications and design targets in this draft. Following draft 2, which I will grade and give you comments and feedback, we have a design review about about 6 weeks after draft 2. Here, by then, you have done transistor level circuit and system design. You can basically we pick a real CMOS IC process, even though it's an old process. I have picked this because the best designs can actually be submitted taped out to MOSIS for fabrication. They do it only for educational classes, educational purposes, such as ECE6414, and the size is limited to 1.5 by 1.5 millimeters. They call it a tiny chip, and I have had students in this class that have fabricated their class project, their chip, and the chip, when the chip comes back, I provide the means to the group to test the chip, and they have been able to publish papers, conference papers, out of their 6414 class. And then one thing I forgot to mention is that for the design review, the team visit me, and we get together and we go over block by block transistor level design. I look at the circuit simulations, and if you have also completed the layout, I look at the post layout simulations, and I grade your design at that time. And the most important part, basically the final results of your project effort will be included in your final project. This is a 10-page paper, and it will be 10 page including the references. It has to be done in IEEE journal format and should be written exactly like a journal paper. This paper will include topics and sections such as literature survey, which should be reflected in the introduction, complete design description, design theory and calculations, complete circuit schematics, circuit layout, pinout diagram, post layout simulation waveforms, testing and measurement procedure, assuming that the chip is fabricated. So basically at the end you have to design for testability, and what you will include in this final report is exactly as if you have received the chip back, just instead of doing actual measurements in the lab, you do post layout simulations. And then you also need to summarize what you have achieved and compare it with the design targets in the summary. I usually encourage teams to also have another column to compare the performance of their circuit with the state of the art. Final presentation will be during the final exam allocated time. You will have 20 minutes each group to present in a conference style. The only difference is that the presentation will be done by the entire group as opposed to only one person. Each presentation will be followed by a 5-minute or more question and answer from the audience, as well as myself and one or two judges that I usually invite to class to see the presentation and ask questions. And I also look at their grade assignments when I grade the final presentation. So the quality and your skills in delivering the presentation is as important as the contents of the presentation. So I highly encourage you to rehearse your presentation and create high quality slides, very professional looking, because at the end, whether you end up in academia or join a company, you need to be able to effectively present your work, and this is a practice for this type of interactions with your boss or with your colleagues or advisor, and so on and so forth. So to summarize, deliverables are draft 1, draft 2, final paper, and final presentation. And this is aside from the weekly, not weekly, but perhaps bi-weekly homework assignments, exams, and other components of this course. Please note that the deliverables, I need to receive them electronically before the due date. After the due date, within 1 day or so, you will be graded from 50%, and if you send the deliverable after the next class, it will not be accepted. These are the most important dates of this semester for your deliverables. So the table is also posted on the syllabus, so please mark them on your calendar and observe them very carefully in order not to lose any points in just delivering these items after the deadline. And also the exams will be the dates of the exams are listed here and also included in the course calendar online. So I will not go through these words of wisdom. I highly encourage you to read them carefully and learn from them, because They come from a lot of experience over a few decades by one of the best IC designers that I know, my good friend Dr. Tim Denison from Medtronic. So with that, I conclude this lecture and this presentation, and invite you to watch the first couple of videos that I will post online, and also read the first paper that I have posted online, and I will see you all next lecture. Thank you very much.